As most of you probably know, there is an increased effort in transitioning from the current non-renewables into a greener energy scenario, and the supply of strategic metals and also common base metals plays a huge role in this strategy. The demand for certain metals is believed to rapidly increase in the near future, and the supply of current known reserves for several of these elements is not enough to meet the demand that is predicted to happen. If this is the first time that you're hearing about this role that mining has in creating a more sustainable energetic future, I advise you to listen to an interview that I had with Dr. Rebecca Paisley. She's a geochemist from the UK. She works in a lithium exploration company, and we talked about the role of exploration and how scientists can impact the future of energy and mining. You can access this chat we had using this QR code, or just look for Nice Chats on Spotify or Apple Podcast, or Google it. All of that will work. And with that in mind, the reason why we're so interested in VHMS is because the VHMS deposits are rich in base metals. So an important source for these metals, which are expected to have their demand increased in the near future. VHMS systems are important source of copper, zinc, lead, gold, and silver. They actually account for more than half of the global production of lead and zinc. And they also contain locally some other important minerals like cobalt, for example, and other strategic metals in certain deposits. VHMS deposits are the result of metal precipitation from a mixing of seawater, pore water, and circulating hydrothermal fluids with a possible additional magmatic component. The most commonly studied process in the formation of VHMS systems is seafloor accumulation of sulfides from the discharge of metals from exhaling hydrothermal fluids. However, subsequent studies have described large-scale subseafloor replacement deposits, both in modern and ancient settings, and particularly in these older VHMS deposits. Doyle and Allen, 2003, they recognized the importance of subseafloor replacement in massive sulfide systems, and then they coined the term replacement type VHMS. And these are deposits which are characterized by the fact that the ore precipitates from volcanic hydrothermal solution within the pre-existing volcanic or sedimentary rock. So they do not contain exhalates, and instead of a seafloor mineralized horizon, commonly they display textures of replacement fronts of the host rock. And because there is often in these deposits not a very clear stratigraphic marker for the timing of mineralization, it's important then in that case to demonstrate that these mineralization is actually volcanic, if that's the case. And therefore, there would be a consequence of that volcanic process and all the fluids involved, and not simply a post-diagenetic process, which is associated possibly with a different form of mineralization mechanism that simply happens to be hosted in this volcanic sequence. And that obviously does not characterize VHMS. Western Australia has great potential for the existence of VHMS deposits. However, I have focused my PhD studies in the Yilgarn Craton, so that's what I'm going to present to you today. The Yilgarn Craton, as most of the audience probably knows, since we are in Australia and not in Europe anymore, is an Archean terrain in Western Australia, illustrated here in the figure in the left. And this map shows also VHMS occurrences, known VHMS occurrences in the Yilgarn, and also other base metal occurrences. And we can clearly see when we compare to another map from a different terrain, which is the Superior Province in Canada, that although these two terrains have a number of similarities, they don't share the same number of known deposits. It's clear that in the Yugard there is a much lower number of discoveries. And there is a number of researchers that believe that the Yugard is simply not well endowed on VHMS deposits. This is an interesting argument to be made. However, we've also demonstrated that in some cases, we are basically not very well suited to find these deposits because some of the more traditional exploration tools that are applied in discovering VHMS deposits are not really efficient in some cases in the Yugard because some of the characteristics like thick coverage and the fact there isn't that much outcrop around really hinders this discovery in this exploration. And in this case, what we should do is aim to develop other strategies for the Yugard and Australia as a whole that are better suited to deal with known occurrences. And ultimately, that will lead to the discovery of new deposits. One example of the successful use of modern techniques in renewing the interest of VHMS exploration in Western Australia and also of having positive outcomes in deposit discovery can be seen here, and in a series of studies that were conducted by my colleague Steve Hollis while he worked with the Geological Survey of Western Australia that are still generating positive results and several publications to this day. So this work's still being put out there. And this is only one example of a series of publications and reports that he has produced recently with colleagues and that are available to the public. One of the strategies that we propose, and that was the theme of my PhD thesis, pretty much the title, is the use of isotopic geochemistry and geochronology to constrain all the processes in place within these replacement type VHMS deposits. With that, what we do is we build a 4D framework for the VHMS system, which will then lead you to understand both ore timing and source of metals, which hopefully will lead to the discovery of new deposits. To illustrate how the strategy works, I'm going to present to you our results from two recent publications on the Nimbus deposit. Unlike other well-known VHMS deposits of the Eastern Goldfields, at Nimbus, the dacite that hosts the mineralization was dated previously by Hollis and collaborators in 2017 to be about 2.7 billion years. It is believed also to be part of the Cambalda sequence. And these authors, they interpret the Cambalda sequence to be the result of plume magmatism. Now, while most other VHMS occurrences have been dated to be about 10 million years younger than 2.7, this one obviously is a bit older, and that's very important because if we can verify that there is actually a mineralizing event happening at that time, this opens a window of opportunity for the discovery of deposits in that stratigraphic slice during time. It also has implications for the prospectivity of plume-related sequences within the Yugard for VHMS deposits. So the question here that we're trying to answer is the ore formation happening with the 2.7 volcanism or later due to a separate process? The first instinct we had is to directly date the mineralization, like Fred was saying in the previous presentation. And we dated the first ore phase, which is massive coliform pyrite, using rhenium osmium. And although we did obtain a reliable age for sulfide precipitation, the resolution was not enough to resolve the issue of the ore timing between the two competing models. We then went again with the same strategy that Fred presented and try to constrain the alteration assemblages in time. And since this alteration could potentially be linked to the same fluid activity that result in our precipitation, this is a valid strategy. And we dated sericite altered plagioclase, which should give us an alteration age. And we obtained these ages at about 2.63 GA, so much younger than the 2.7. That age was not only recorded by these altered plagioclases, but also on monazites from a polymict conglomerate on the hanging wall sequence. And in the case of a metasedimentary rock like this one, the monazite is either detrital or metamorphic, and in this case, the relationship between the crystal and the foliation suggests that these are metamorphic and formed at the time of the deformation. What our argon-argon results and monazite ages show us is that the alteration that was recorded by these minerals is much younger than the magmatism that formed the host dacites. Now, if this alteration is related to the main mineralization event, that is an indication that the ore is actually post-magmatic, which would favor a second non-VHMS model for this deposit. So what we know right now at this point is that the syn-volcanic VHMS would have been developed shortly after the formation of the host stratigraphy at about 2.7 GA. That's correlatable in time with a high temperature setting that is responsible for a large volume of magmatism within the Yilgarn Craton. The second model is some sort of post-diagenetic replacement, and that would be constrained by the alteration at about 2640 million years. And this coincides also with the occurrence of low calcium granites and the M3 metamorphism in the Yilgarn, which records several localized gold mineralization events. So we still need to decide which of these models is the right one. And to try and do that, we actually moved away from geochronology a little bit in a certain way. And we decided, however, to use our multidisciplinary approach and have a look at another ore sulfide from an isotopic geochemist kind of point of view. What we did is we used a highly precise double spike method to measure the lead isotopes in Galena. And because of the precision, we were able to observe chemical differences between the two different types of galenas that we looked at. Because of the amount of lead in Galena, which is huge, we only needed very small quantities of this material, which meant that we could analyze very tiny vein-associated Galena crystals. And even we've developed this quasi in situ sampling method, where we just put a little drop into the thin section that reacts readily with Galena. The HBr that we used reacts readily with Galena, but it doesn't react so quickly with other sulfides. So we then suck the solution back up with a little pipette, and we put it in straight into a test tube for analysis. The lead isotopes indicated that the two different types of galenas were formed in different moments in time. The galena associated to the polymetallic ore phase, which is the main mineralization stage, represented here in figure A, has a very homogeneous lead isotope composition. So it forms a little cluster that we call in this figure here ore cluster, right there at the bottom left. And the second type of galena are actually distal to the mineralization, and it occurs in late quartz carbonate veins that can be seen here in figures B and C. And they often crosscut the main foliation. These late galenas, unlike the ore cluster ones, they show this mixed compositions, which we interpreted to be likely the result of three sources of lead. The first one would be the ore cluster, which indicates then that there was some remobilized lead from previous sulfide phases when you crystallize these younger galenas. an older component, which is likely sourced from nearby sediments. And finally, in order to produce this mixing line here, there has to be contribution from lead that is derived from an evolved source. So younger lead is necessary to produce this mixing, and that has to be younger than 2.7 Ga. We have, as I showed, well-constrained ages for two major geological occurrences at Nimbus, one at 2.7 Ga, and then a later alteration around 2.6463. And we believe that it is very likely that the Galena were crystallized at those times, and that the cluster Galena would be related to the 2.7 event, while the later Galena was formed with the alteration, and therefore has mixed source of lead. This indicates that the main ore assemblage was likely formed with the 2.7 Ga volcanic activity. And as far as timing is concerned, it does point towards a synvolcanic subsea floor replacement. Furthermore, when you correlate the position of the Galena towards the ore of the high ore zones, the proportion of lead from the ore cluster seems to be smaller the further you get away from these high ore zones. And that has a good potential to be developed into vectoring tool towards these high-grade ores. However, you can see we have only 3 points, and further studies are definitely required in order to demonstrate that this potential exists and if it can be applied. So in summary, so far, the VHMS model fits the timing of ore formation according to our results for the Nimbus deposit, which determined the 2.7 Ga Kambalda sequence as fertile for these types of deposits. And we also got an added bonus of the lead composition of Galena having potential vector towards high-grade ore. We also looked at the metasedimentary rocks that hosted the monazites, if you remember, that are hanging wall to the host dacite. And this sedimentary succession contains black shales with these beautiful nodular massive pyrites, which are sedimentary in nature. We were able to combine the renim data of both black shale and nodular pyrite to calculate an isochron age at about 2680. Unfortunately, there are some limitations to the renim technique, which meant that we couldn't obtain as good a resolution as we'd hope, and therefore we can't irrefutably demonstrate the timing of the mineralization in relation to the deposition of the succession of sedimentary rocks. However, what we do observe in the record is this increased metal content within what we called an enriched interval. So you can see that here at the bottom right, within the sedimentary succession. So you have an increase of overall trace element content and some interesting ratios that are indicative that there is an increase in metals in seawater that is related to the supply of metals to the mineral system. And this increase of metals in seawater is recorded by the marine pyrite, and it is an indirect evidence for the synvolcanic timing of ore. You can get way more details than this about our arguments and the evidence that we have for saying this is sedimentary pyrite from the paper we published in Mineralium Deposita. This study demonstrates, this part of the study about trace elements demonstrates the value of pyrites as a tracker of trace element chemistry, and that can't be replicated by traditional whole rock geochemistry, as our diagram here demonstrates. Pyrite has a great potential to be developed into an exploration tool. That's nothing new. This line of study has been recently developed by several working groups. However, this study does present an example of the use of mineral chemistry for sedimentary pyrite, as well as the traditional massive sulfide-related pyrites. In fact, the development of new indicator minerals for exploration with the use of advanced techniques such as laser ablation and other isotopic and geochemical studies, or even the TEMA, right? The automated mineralogy is something that has gained a lot of attention, not only at the John Delater Center and Curtin University, but in Europe as well. So to sum up, in addition to what I've already summarized before, obviously the VHMS, according to us, fits the timing of ore formation, but also the trace element composition of sedimentary pyrite does track times of mineral activities in this nearby succession, and you could have a potential for exploration value. And the most important thing, which is very complementary to something that Fred said in his presentation, is that this multidisciplinary approach was vital in getting conclusive results. So he said about, the best thing to do is always to get more information about different geochronometers. And in our case, that proved to be essential because if you look at only one of these components separately, you might get a wrong answer, or you might not get the answer or the complete picture. Lucky for me, although I did have to utilize a bunch of different techniques, I did manage to do most of my analytical work within the JDL facilities because there are a bunch of different instruments and techniques in place. So all of these techniques that I presented here and more, I undertook when I was there at Curtin University, which is a very rare privilege, I now realize. If you want to see another example that we have of applying the same methodology, but this time to a different deposit, we have another paper that was published last year. And I'm happy to take questions now. Please go and have a look at our publications that came out last year and earlier this year. And thank you for inviting me again.